Moment of inertia for composite areas. Many engineering members, such as this I-beam, are shapes made up of several component shapes. For this instance, 3 rectangles. To analyze shapes such as these, we break the composite area up into component areas, or even void areas, and use the basic formula for I of those shapes. This is kind of like that game where the different shapes are falling from the top and you have to rotate them and get them to fit together exactly right so you get the most efficient stack. And if it reaches all the way to the top, you lose the game. You know that game. It's like that. We're trying to say that this shape is, a horizontal rectangle, a vertical rectangle, and a horizontal rectangle. We know the moment of inertia equation is BH cubed over 12 for each one of those individual shapes, and then apply the parallel axis theorem because we know that BH cubed over 12 is the moment of inertia of, say, this rectangle here. It's going to be, its moment of inertia about its x centroidal axis would be B sub f times T sub f cubed over 12, but that would be about this axis right here. So then we multiply by that distance squared times the area of that shape, and that would give us the moment of inertia of this one. We do the same for all 3, add them all up, and then we get the moment of inertia of the composite area. So that's the idea that we're doing here. So we're going to use that parallel axis theorem. So again, this is where I'm saying we're kind of using that first method with tables. Because it's not always going to be rectangles. You might have semicircles or quarter circles or circular segments or rings or, triangles, all kinds of stuff. And you look them up in the tables, and then that will give you the moment of inertia of that about its own centroidal axis. Find the difference between its centroidal axis and your overall shape centroidal axis. Apply the parallel axis theorem, and you've got it. So pretty easy. Just as a reminder, those tables are all over the place, the internet, the FE handbook. They give you that moment of inertia about the centroidal axis of that shape because that's all it would know. It might give you another one like the rectangle BH cubed over 3 term, but for the most part, they usually only give you the one about its own centroidal axis. So you're going to start with that and modify it as needed to build your shape. So this is what it kind of looks like. It's very similar to what we were doing with our integration. It's just a summation as opposed to an integral symbol. So here we're, N is the number of component areas. ICI is that's what you're going to look up in the table. So, moment of inertia about the own centroidal axis for this rectangle up here. That's maybe IC1, right? And then you got IC2 would be this one. IC3 would be this one. And to that, you add the area times the distance between their centroidal axis and the overall axis that you're trying to find the moment of inertia about, and square that. A is the area of the component area, pretty basic. There's that distance that we just talked about. I like to do it as a table, and I strongly urge you to do that as well, because if you do it as a summation of a bunch of values, you just do this long strung out equation, you'll forget a value somewhere. So the table makes sure you hit it all. So my first column here, my very first column, I describe the component area. Then I give the moment of inertia of that component area about its own centroidal axis. Then I calculate the area of that component area. Then I calculate the distance between its centroid and the overall axis that we're summing moments of inertia about. And then this column here, this a sub I d sub I squared, is really just that column there times the square of this column. So this is really just kind of Excel almost right here. And then you add the first column and the last column together to get this column here. And then you sum this column up down here, and that gives you your total moment of inertia. So really straightforward. Things to remember when you make your component areas: you cannot miss area, omit area, and you cannot double count area. So when we're talking about rectangles, if we go all the way across here and all the way across down here, then our other rectangle has to go from that intersection up to this intersection. You can't use the total h. The height of this rectangle right here would be h minus TF, for instance. You cannot double count area. Your table is going to have as many rows as you have component area. So I show 3 here. You might have 13 if it's a big complex shape. It usually can do it in a few different component areas, 2 or 3, 4 max, something like that. And then, again, you just sum all this stuff up, and that gives you the I for the overall shape. Final thoughts. Again, draw the picture, label it. The biggest thing I think that people make mistakes on is this D distance. It is so basic, but until you draw this diagram and label it, the D distances are not going to be apparent. For instance, the D distance for this horizontal rectangle up here, if we do it like that, will be the center of this one, which will be down to this line here. If we're finding the moment of inertia about this line, it would be h over 2 minus tf over 2, because you got to get to the center of this shape. You'll see it. I'm going to work an example that goes through this whole thing. But drawing it is really important, and using that table because you don't miss anything then. And another note, it can be any axis required. When I say what's the moment of inertia, I could have picked the moment of inertia about the bottom edge here or the top edge or any axis, but oftentimes it is that overall shape's centroidal axis. And that's because of the applications in further mechanics. Like when I was talking about you standing on the 2x10 board at the beginning, the moment of inertia about the overall shape's centroidal axis becomes very important. So you just trust me on that for now. But we're oftentimes finding that moment of inertia about the centroidal axis, which means that this and centroid go hand in hand. If I gave you an I-beam, you would have to find that centroidal axis first. You'd calculate it through centroid, or possibly just looking at the symmetry like you see here. But whatever shape I'm giving you, you would have to find the centroid, and then set that as your axis and find the moment of inertia about that axis. The cool thing is when you're doing those back to back, centroid has a lot of the same values in it, like the areas here. There's a lot of things, even how you diagram it is very similar to how we did it for centroid. So there's a lot of you get to reuse numbers over and over again. So it's really nice if you're doing it all at the same time. If your component shaped centroid lies on the same line as the axis you are finding moment of inertia about, then there is no parallel axis term, right? It's 0. That can be really cool when you're building a big table. If you have a 0 here in your D column, you don't even need to calculate the area for that shape, right? Because you know that AD squared is going to be 0, so you don't have to calculate this, and this summation of the row here is just going to be your first value. So it's really cool when you can get that D distance to be equal to 0. The more practice you get with doing these types of problems, you'll start to see, oh, if I use these shapes, then I will have that issue come up, and it will make it much easier for me. You'll start to get the hang of it. We'll work an example 2 different ways. One time we take advantage of that, and one time we don't, and you can see the difference. Void areas are a great hack for this method as well. Just note that their ICI, that their moment of inertias, are always negative, as is their area. So all their value, this right here of say component area 2 is a void area, then this would be a negative moment of inertia. It would have a negative area, which means that this AD squared would also be negative, which means then that all of this over here would be negative. You're basically, and what I mean by a void is one of the things we'll do is we'll look at this as an overall rectangle and then subtract back out these voids. So we kind of overshoot our area and then pull back. So we overshoot our moment of inertia and we adjust it by negating some of it. And that can be very beneficial. You might be like, why do we overshoot and then come back and adjust? It can make some of your calculations much easier.